All right, let's dive right in. Welcome to this explainer, where we're tackling Chapter 2 of Martin Kleppmann's Designing Data-Intensive Applications, focusing specifically on graph-like data models. If you're building applications today, you already know that data isn't just about isolated facts sitting neatly in a table anymore. It's entirely about the complex, messy web of relationships between those facts. And Chapter 2 breaks down exactly why we need specialized models to handle all that complexity.
So here is the ultimate connectivity conundrum. How do you actually store your data when literally everything is connected to everything else? If you've ever wondered how your favorite social apps instantly know exactly who your mutual friends are, or how a mapping system calculates the shortest route to a coffee shop in milliseconds, you are bumping right into this exact problem. In these systems, the connections between the data points are just as important, if not more important, than the data itself.
So here's our roadmap for today's explainer. We'll start with the many-to-many problem, then we'll introduce the graph model, dive into property graphs, explore the triple store approach, and finally, look at how we actually query the graph.
Part 1. The many-to-many problem. Let's talk about the absolute limits of tables.
Look, document databases, they are absolutely fantastic for self-contained one-to-many data, like a resume or a user profile. But when things get tangled, yikes. And traditional relational databases, sure, they handle simple many-to-many relationships fine, using foreign keys at first, but as those connections multiply, your application code just gets bogged down in cumbersome, incredibly slow joins. You basically end up having to shred your data into dozens of tiny tables, which makes everything incredibly complicated.
Which brings us to Part 2, the graph model, connecting the dots.
When everything becomes potentially related to everything else, it is time to leave tables behind entirely. Think about a scenario with two people, Lucy and Alain. They're married. They were born in different places, Idaho and France, but both are currently living in London. A graph handles this beautifully. Notice how it effortlessly manages varying levels of detail. Lucy's birthplace is a state, Alain's is a city, yet they snap perfectly into larger geographic structures like North America and Europe. Imagine trying to model all of those overlapping, heterogeneous relationships in a standard SQL schema without completely losing your mind.
At its core, a graph is just beautifully simple. It's built from exactly two things: vertices, which are your entities, and edges, which are the relationships connecting them. And the real magic here? A single graph can store completely different types of objects together. Take Facebook, for example. They maintain a single massive graph where people, locations, events, and check-ins all coexist, with the edges describing exactly how they interact with one another.
All right, Part 3. Property graphs, vertices and edges. In Chapter 2, Kleppmann highlights two primary ways to actually structure this graph data. We're going to start by looking at property graphs, famously implemented by systems like Neo4j, before we compare them to triple stores, which you'd find in databases like Datomic. With a property graph, you can basically say goodbye to strict, restrictive schemas. A vertex can hold whatever key-value properties you want. And the edges? They simply connect a tail vertex to a head vertex with a label describing that specific relationship. Because those edges track both their start and end points, you can zip back and forth through your data instantly. It means as your app evolves, you just add new types of relationships without ever having to migrate some rigid database schema.
A quick side note, I want to clear up a historical myth right here. Modern graph databases are not just the 1970s Codasol network model in disguise. While Codasol also tried to solve the many-to-many problem, it was incredibly rigid. It forced strict schemas and made developers write super fragile imperative code just to navigate access paths. Today's graphs are a totally different beast. There are zero schema restrictions, you can query any vertex directly by its ID, and they use high-level declarative query languages that make your life infinitely easier.
Moving on to Part 4, the triple store approach. Triples and statements. This second major model achieves the exact same connectivity goals but uses a slightly different vocabulary. What's super fascinating about a triple store is how it breaks literally every piece of complex information down into a simple three-part statement: subject, predicate, and object. It reads exactly like a basic English sentence. Jim likes bananas. Lucy is married to Elaine. It's incredibly straightforward.
And that object part of the triple, it could be a simple primitive data type, like Lucy's age being 33, or a connection to a totally different vertex entirely, like Lucy being married to Elaine. This highly standardized format builds out the exact same massive, complex webs we just talked about.
It's often written line by line in a format called Turtle, which allows developers to construct these vast interconnected networks statement by statement.
Finally, Part 5, Querying the Graph, extracting those insights.
Because let's face it, all this beautifully linked data is totally useless if we can't effectively ask it questions. To extract information from property graphs, the absolute standout declarative language is Cypher. Fun fact from the source text, it's actually named after the character in the movie The Matrix, not cryptography. Because it's declarative, you literally just tell the database what pattern you're looking for, and the query optimizer does all the heavy lifting to find the most efficient path.
Cypher is incredibly clever. It uses ASCII art-style arrows to visually map out exactly how it traverses the edges. In this snippet, you can literally see an arrow pointing from Idaho over to the USA, with the relationship labeled within. It's just so intuitive to read and write.
Now, I know what you might be thinking. Can I just use standard SQL to query my graph? Well, theoretically, yes. But trust me, you really don't want to. Since the number of connections between two nodes can totally vary, like a city being inside a region, which is inside a state, which is inside a country, SQL requires these messy, variable-length recursive queries to follow the paths. You are talking dozens of clunky lines of SQL code to accomplish what Cypher knocks out cleanly in just 4 lines.
But what if you opted for the triple store model instead of a property graph? Well, you wouldn't use Cypher. You'd likely jump into Sparkle. This language is custom-built specifically for those subject-predicate-object relationships we discussed, allowing you to easily filter and match semantic patterns across massive webs of data.
Or, alternatively, there's Datalog. This provides a generalized, rule-based approach for querying that is highly favored in academic computer science and used in systems like Datomic. It's actually a subset of the programming language Prolog. It basically works by matching variables across logical rules to deduce these really complex relationships step by step.
But honestly, regardless of which language you choose, Cypher, Sparkle, or Datalog, querying a graph is essentially just navigating a city map. You start at a no location, you drive down the connected roads, which are your edges, and you just filter your paths based on the labels you care about until you arrive at your destination.
Which wraps up our explainer on Chapter 2's graph-like data models. But I want to leave you with this final thought. The very next time you get a shockingly accurate friend recommendation or your navigation app instantly reroutes you around a massive traffic jam, start looking for those invisible edges connecting everything in your digital life. The world isn't a flat table, folks. It's a graph. Thanks so much for learning with me today, and I'll catch you in the next explainer.